Hello, everyone. My name is Higueros. I am currently a PhD candidate at Duke University, studying mechanical engineering and material science under the guidance of Dr. Po Chun-Shu. Today, I will be discussing my project, Vascular-Enabled Advanced Electrodes for Fast Charging Lithium-Ion Batteries. My research pertains to energy storage, particularly fast charging batteries. Fast charging is important for electric vehicles to reduce driving anxiety that some consumers may feel, to increase the charging rates of handheld electronics, and of course, to improve batteries used for extravehicular activity suits in space. Performances of batteries at high charging rates, or in other words, high C rates, decline as a result of structural instability of anodes, which can be seen through delamination effects, poor ionic diffusion, and other mechanisms that I do not describe in this presentation. In the past, 3D electrodes have been designed to improve the performance, and they have because of increased surface area as well as a decrease in ionic torch velocity. This just means that the lithium ions were actually found to have a path that is easier to travel with in 3D electrodes. However, these structures tend to be periodic or at times can be random. And so we have to ask ourselves, is there an optimal pore configuration for batteries at fast charging rates? In addition, we also want to understand how pore configuration alone will impact the performance of batteries, right? So increasing the degree of freedom in our pore configuration. We look to nature for inspiration and find this vascular transportation system in almost all forms of life, in our lungs, in plants for water and mineral transport. And we want to know if we can also apply the same structure to electrodes in lithium-ion batteries. Of course, we can't just create a vascular structure and apply this to batteries because, again, this will be random. And also, if we try different structures, it would take forever to make and characterize. Hence, we used artificial intelligence to create a forward design process and an forward prediction process and an inverse design procedure to find this optimal pore configuration that looks like that has a vascular structure nature to it. We use CONSOL to simulate several different structures in electrodes and characterize their performance. We use neural networks to increase this data pace, and then looking at the highest performing unit cell, we then, through an inverse design process, found this optimal pore configuration. We then compared its performance with the performance of electrodes that contained either vertical channels or no channels at all, which for the no channel system, this is what is typically seen in commercial lithium-ion batteries. The second part of the project was to actually fabricate the electrodes. This was my part of the project, and so by using 2D micromanufacturing methods, I was able to create sacrificial vascular templates with submicron features. These templates are pre-magnetized and then placed in isopropyl alcohol, which can be seen on the left. Using an external magnetic field, we then align these templates. I drop test the slurry, which contains the active material in the electrodes, sinter at 900 degrees Celsius. And through this fabrication process, I am able to create a vascular pore configuration within our electrodes. On the right, you can see this pore configuration through scanning electron microscope images. And so our next steps are to characterize our electrodes and then compare it with electrodes that contain either no channels or, again, vertical channels, just as we did for our simulation. And we hypothesized that the vascular pore configuration will indeed improve performance of batteries at fast charging rates. Thank you so much for listening to my presentation, and I will now open the floor to any questions.